Hello and welcome to this Isaac overview video on mechanics as it is taught within an A-level course. We are particularly covering those aspects of mechanics that are usually taught in Year 12 in this video. Please bear in mind this video is just part of the resources available to you through the Isaac Physics website and indeed with the books that are available too. So if there are particular concepts that you want further help with, please do go to the relevant pages where you will find extra explanations, further videos, questions to practice and help available to you. The first thing you need to be aware of is that quantities can be vectors or they can be scalars depending on whether they have direction or whether they have size alone. And you need to be aware of the lists of the relevant quantities. There are two things you need to be able to do with vectors. The first thing is you need to be able to split them, that is resolve them into what we call components. So if we look at this vector here that's drawn by the black L, it has a horizontal part there and a vertical part there, and sometimes we just want to know what the horizontal part is or we just want to know the vertical part, and we use trigonometry to help us work it out. So this one we multiply by the sine of the angle, this one we multiply by the cosine of the angle. Now, while usually we will be splitting something into horizontal and vertical components, sometimes we'll have an object, for example, on a surface, and the force itself may well be vertical. However, what we want to know is what fraction of that is, if you like, parallel or perpendicular to a surface. So then we would be resolving like this. The two components are at right angles to each other, but notice now they are not horizontal or vertical. They are parallel to or perpendicular to a surface. So the triangle doesn't always have horizontal and vertical parts. Sometimes they are at diagonal angles. Now this is the first slide on which I hand over to you to do some practice. If you're doing this in a classroom or indeed in your own room, you may want to pause the screen now so that you can have a go at these. There are separate videos on the same page that show all these questions being worked through, and I would like to point out that whenever we have a practice session, it will always say at the top where you can find further resources to help explain this concept if you need more explanation or further practice starting at a simple level and working its way up. These are available on the Isaac website, and if you are looking where the answer video is, you will find direct links to those sites and those explanations and tutorials. So if one thing you need to be able to do with vectors is break them down into their components, the other thing you need to be able to do is add them up. And there is one area which often catches people out. They'll be presented with a situation like this where an object is subject to two forces. There's a vertical force and there's a horizontal force. And the person will be asked what is the resultant force. In other words, what is the one force that would do the job of both of those? And although this, if joined up, would make a triangle, we do not use that as a resultant. That is not how it works. What we have to do is we have to move one of the arrows, move one of the force arrows, so that the arrows are joined nose to tail. So here's number one, and then we start number two where number one ended. And then the journey from the very beginning to the very end, that is the beginning of number one to the end of number two, is what we call the vector sum. Sometimes, particularly when talking about forces, we also call it a resultant. So the first thing you have to do is never mind where the lines of actions of the forces actually are, move them until they form this nose to tail pattern. Here's an example where four forces have been added up, and you can see each one is added on to the end of the previous one, and the total of all those forces is the black line here that goes from the beginning of number one to the end of number four. Sometimes it's the case that when you put all four arrows together, you come back to where you started, and in effect there is no black line. They formed a complete loop. When that is the case, the vectors have added to zero. There is no resultant force in this case. And that's one of the things that is needed if, for example, a situation is going to be in equilibrium and not start moving anywhere. But more of that later. So here is some practice, and here are instructions for each of these scenarios in terms of putting the knowledge into practice. Two of these are drawn from aviation, where you'll see it mentions things like ground speed and air speed. Airspeed is the vector of the motion of an aircraft through the air in which it is travelling. The speedometer or airspeed indicator in the aircraft measures that, and the engine can give a certain airspeed. Ground speed, on the other hand, is the velocity of the aircraft over the ground, and that is what matters when you're trying to work out how long it's going to take you to get to your destination. I mention that because although they are called ground speed and air speed, they are in fact velocities. They do have a direction as well as a magnitude. I'm afraid just within the aviation community, those words, which are easier to say than ground velocity and air velocity, have gained credence. So that's why I call them that, but please, they are actually velocities. So have a practice, and remember, there's a video showing these worked through on the same website which you can use. By all means, pause it now so you can have a go at these questions. Having looked at vectors, we now look at how you describe motion. And if you're doing maths A-level, you may well encounter a lot of these ideas as part of your A-level maths as well. So we talk about displacement. That's the position, if you like, of the object. It's not just how far it's moved, but also in which direction. When things are moving in one dimension, we often plot a graph. We show where it is as a function of time. At any time where it's stationary, the line will be horizontal, and the faster it goes, the steeper the line. In fact, we can measure the gradient of that line, and it tells us the velocity. But you should be aware that there are two kinds of velocities that you can face in an A-level course, and they're shown in this graph here. So here we have an object, and there is its displacement time graph, and you see it's curving upwards, and that means that it's accelerating, it's getting faster. Now let's suppose we're interested at this point here. We could be interested in what we call the average velocity, which is on average how many meters a second has it travelled in this part of the graph. That would be the gradient of what we call this chord here that lines this point up with the origin, and that would be an average velocity. However, if we were looking at the speedometer on the object, it wouldn't be interested in what the velocity had been previously or any kind of average. It would be what is the velocity now. And if we wanted that, we would look at the steepness of the line at that particular point. We draw a straight line fitting with it, we call that a tangent, and we measure the gradient of that. And that would give what we call the instantaneous velocity. So you do just need to be aware of those differences. So velocity, we call it the rate of change of displacement. In other words, how much does this displacement change each second? And when we're using letters, whereas displacement is usually given the letter S, it is occasionally given D, but it's usually given an S. Velocities are often given U and V. So you have a starting velocity, U, and a final velocity, V. I've already said that the displacement covered will be the average velocity multiplied the time, and if the velocity is changing uniformly, in other words we have a constant acceleration, there is a steady change of velocity, then the average velocity is given by the mean of the starting and finishing velocity. So we have this equation here for the displacement covered as something goes from velocity u to velocity v. We can also have velocity time graphs where we plot velocity on the vertical and time on the horizontal, and under those circumstances the area under the graph gives the distance travelled, or I should say the displacement travelled. If it's above the time axis, it's sort of positive. Below the axis, it's as if you're going backwards, so that counts negatively. Acceleration, as I'm sure you're aware from GCSE, is how rapidly the velocity is changing. So if we have, for example, an acceleration of 5 meters per second squared, what that means is every second you gain 5 meters per second of velocity. So if you started at 0, 1 second later it would be 5, another second later it would be 10, then 15, then 20, then 25, every second gaining 5 meters a second of velocity. So acceleration being that rate of change, it's the gradient of the velocity time graph. So in other words, it's the new velocity minus the old velocity, that gives the change, divided by the time taken, a formula I'm sure you are familiar with from your previous study. However, at A-level, we do put it together to make some more complicated equations, which are used in situations where the acceleration is constant. So, for example, something falling under the action of weight alone, the interaction of gravitational forces with that object. But other kinds of constant forces will also work, where you've got an engine that is able to pull an object with a steady force. So, you've already got the equation S equals average velocity times time, and you've also already got the equation that acceleration is the change in velocity divided by the time, which, by the way, can be rearranged to look like that. But putting the two equations together, as shown there, you don't need to be able to do that in the exam, but you do need to be familiar with the final results, albeit they will be given on your formula sheet, that you've got two expressions for the distance, or the displacement I should say, moved by an object. Here's one in terms of the time, and here's another one in terms of the final and starting velocities. And if the right equation is selected, we can solve a problem. So here we go, calculate the displacement if we're accelerating from rest to 50 meters a second with an acceleration of 6 meters a second every second. Notice that we've got we've got A, U and V. We want to know S. The quantity that we don't care about is T. There is no involvement of time anywhere here. So that helps us choose the equation. We look for the equation that's got no T in it, and that's this equation here. The lovely thing is it's already got S as its subject, so we can use that equation, we can put the numbers into it, and it will give us our answer. Sometimes, however, we have to rearrange the equation before we can get to the solution, but that is how we go about it. So here are some for you to try. And there are some resources you can use to follow things up if you wish. Please pause the video, have a go at this, and when you want to check your answers, please look on the website and you'll see a video where these questions are worked through. The bouncing ball is a scenario that examiners love to test you on. Here is a displacement, or in this case height, vertical displacement, time graph for a ball that is dropped from a certain height, let's say 3 meters, onto a surface. So it comes down, you see it speeds up as it comes down, look, the line's getting steeper, and then it bounces, but it doesn't quite bounce as high as it came from, and then it bounces again. And you're expected not only to know this graph, but also what the velocity time graph looks for this scenario. I'm going to explain this one as part of this video, but I just want to give you an opportunity to sketch what you think the velocity time graph will look like before you see it on the screen. So just give you an opportunity to pause if you want to try and work it out for yourself. And now what I'm going to do is show the answer. So this is what the velocity time graph looks like. I've used the convention that negative velocities are when the ball is falling and positive velocities are when it is rising. So this is the section where you can see the ball is falling, albeit with increasing speed. It's dropped. Initially it's not moving, but the velocity gets more and more downwards, that's more and more negative, until eventually the ball hits the ground. At that point, the bounce, the force involved with the bounce, switches the velocity from being negative, downwards, to positive, upwards, but it's not quite as positive as it used to be negative, because some energy that was stored in the, if you like, the kinetic energy of the ball has come out as thermal energy. The ball has heated up. You'll be particularly aware of that if you play squash and you notice the ball getting hotter as you play. So we've switched the velocity, it's now positive, and that's what causes it to rise. So that is the ball just after the bounce. Now, as it goes up, it slows down. And then it reaches its peak, the highest it ever goes. That's where it's momentarily stationary, and then it gets faster and faster on the way down. Notice that the business of slowing down and then speeding up is one continual line on the velocity time graph. And then we have another bounce as before. The area in these triangles, so this triangle here, represents the distance fallen by the ball, in other words, the height it was dropped from. You will notice it rises to a lower height, and therefore the area in this triangle is going to be smaller than the area in this one. However, the height risen here is equal to the height lost here. So therefore that triangle and that triangle have to have the same area. So note the points of this graph and remember that at all times where the ball is not hitting the ground, it is just in the air being acted on by its own weight, the line shows that acceleration due to gravity at negative 9.8 meters per second every second, and that's why you get these parallel lines here. It is worth knowing that one. They do examine that one pretty frequently. Once you've got the hang of analysing motion in one dimension, you then have to deal with two. So that is where you've got, for example, horizontal motion and vertical motion. And the key thing to learn there is that the two are separate. So if we take an equation like the good old S equals ut plus half at squared, then we have to remember that if we're applying this in the vertical direction, then all of the quantities, that is displacement, velocity, acceleration, are all vertical. We mustn't mix up and have some horizontal quantities as well as vertical quantities. It must be either all y's or all x's. There is one exception to that, and that is the time. The time, it's a scalar, it's completely outside of the dimensionality of this problem, and that will be the same in the horizontal and vertical parts. But all the other things, the accelerations, the velocities, the displacements, must all be either horizontal or vertical, but you must not mix them up. Now, in the problems you're given, nearly always the only force acting will be gravity, and therefore there'll be a downwards acceleration because of the gravitational attraction of the Earth and your object. However, you will hardly ever be given a situation where there's any horizontal acceleration. So the acceleration in the x direction is 0, and therefore the analysis in the x direction is much more straightforward. It is just displacement is velocity times time. So let's look at how we would solve a problem like this. A ball is thrown horizontally at 4.5 meters per second from a height of 2.5 meters. How high is it after it's been in the air for 0.3 seconds? I would encourage, while you're getting the hang of these kind of questions, to draw yourself a kind of grid where we've got the vertical motion on one side, the horizontal motion on the other. Notice there's no acceleration in the horizontal direction, and I've simplified things a bit by taking g as 10. My apologies if that bothers you. Okay, and then we fill in what else we know. The time, remember, transcends ideas of vertical and horizontal directions, so that's just goes all the way across. So we're told that it's thrown horizontally. Now, because it's thrown horizontally, it means initially there is no vertical velocity, and that's where this 0 comes from. And that's what often catches people out. They see the 4.5 and think they have to put it there, but it's not, because it's a horizontal motion. The 4.5 goes there. The vertical velocity is initially 0 because we're told the ball is thrown horizontally. We're told that it's thrown from a height of 2.5 meters, and how high is it after it's been in the air for 0.3 seconds? So the time is 0.3 seconds, and if we want to know its height, then we are going to be working out the vertical displacement. So in other words, what we're going to do is we're going to work in the vertical section, because you can see we know three things. We know the acceleration, we know the initial velocity, and we know the time. And given those three things, we could use the equation to work out the displacement. And once we got that, given we know that it started at a height of 2.5 meters, we would be able to work out how high it was after the 0.3 of a second. So we use effectively this equation here, yeah, where S is the, if you like, the distance by which it has moved up or down. Uy, as we see there, is 0. Ay is negative 10. T is 0.3. You put this in and it'll come out negative, and it'll tell you how much the height has dropped. And that height has been dropped from 2.5. So that would be my suggested way into the problem. It does take people a bit of time to get used to that, so don't worry if you have to go through this a couple of times. I am going to work a full example for you in a moment. Sometimes, to make things more interesting, they will give you a situation where the initial velocity is at a diagonal angle. In other words, it's not initially horizontal or vertical. And what you have to do is then split that velocity into a horizontal part. In this case, it would be u cos theta, and a vertical part, that would be u sine theta. Now, the horizontal velocity will just stay the same because there are no horizontal forces. The vertical velocity, however, will be affected by the effect of gravity. So we will have the initial velocity uy negative because it's downwards, times g times t, and remember that the initial vertical velocity was u sine theta. So we have an equation, time-dependent equation here for the vertical velocity, and you may need to do something like that in the harder A-level questions. So let's give an example of one of those questions, and we'll work this one through together. Of course, you can pause the video and do it yourself if you like, but we will be working this one through together. And it's at a ball that's thrown at this speed at an angle of 50 degrees to the ground, and we'll work out the maximum height and the landing point. Let us work this question through. So the first thing we have to do is to work out the maximum height reached by the ball. And let's fill in this grid. So we know the ball is thrown at 14 meters per second at an angle of 50 degrees to the ground, and I've shown this here. And that enables us to work out the vertical and horizontal components of that initial velocity. So this one will be 14 times the sine of 50 degrees, and this one 14 times the cosine of 50 degrees. And we can then put those numbers in the table. So the vertical velocity is 10.7 meters per second, whereas the horizontal velocity is 9 meters per second. Now it asks us the maximum height. In other words, it's asking us how high it goes. And what is clear from that is that we don't really have to worry about the right-hand side of this table at all. We can just work in the left-hand side. We are not concerned about the time, but we do need one more piece of information. It does say maximum height. Well, when the ball is at the very, very top of its trajectory, its vertical motion, its vertical velocity will be 0. It will neither be going up nor down. So we now have 3 pieces of information and the 4th one that we want. So remember, we have v squared equals u squared plus 2as. We're applying this vertically, so I'm just going to put little y's there to remind us, and then we can substitute the numbers into the equation. So I have vy is 0, and that must equal uy squared, that's 10.7 all squared, plus 2a. Now a is negative, so I'm going to change that plus sign for a minus sign to take that into account. 2 times 9.8 times s here, and I should say sy, so that enables us to work out the height. So rearranging, the maximum height sy will equal 10.7 all squared divided by 2 times 9.8. So let's do that. So 10.7 all squared divided by twice 9.8, and it gives an answer of 5.84. And that means I can put my answer in here, 5.84 meters per second. It then goes and asks how far from the start will it be when it lands? Well, I'm afraid I'm going to use a little trick here. I'm going to work out the time it took to get to its maximum height. So I'm actually going to work out the time for this part of the motion. Now I know we did work the distance out, but we have got an acceleration, an initial speed, initial velocity I should say, final velocity. So I'm going to use the equation that says final velocity equals initial velocity plus acceleration times time. I can rearrange to get the time is equal to the change in velocity, that's vy minus uy, all divided by the acceleration. Here vy is 0, so negative uy is going to be negative 10.7, and the acceleration, as we know, is negative 9.8. So if I work that out, I get a time of 1.09 seconds taken to get to the top. So if it takes that time to get to the top, it'll take an equal time to get to the bottom. So the total time to landing is going to be twice that, which is 2.18 seconds. And that enables me to work out the distance to landing. Is going to equal the horizontal speed, which we know as 9.00 meters per second, multiplied by the time, 2.18 seconds, which gives an answer of 19.7. So that tells us how far the object is going to go up, it's going to come down, and they're going to be 19.7 metres along there. And that is how we solve a question like this one. Now it is over for you to do some practice. Here are a couple of questions about 2D motion. Remember, you can get extra practice material and explanations from the Isaac website here, and there is a click link next to the answer video if you want to go there to get extra help. So all the very best with this. Having described momentum, we now look at the role of force and motion, and a key concept there is the idea of momentum. And even at A level, you will sometimes get a question that just says, what is momentum? And they want you to say mass times velocity. Notice it's velocity, not speed. Momentum is a vector quantity, and it's accordingly measured in kilogram meters per second, which is equivalent to the Newton second. It's also worth pointing out that internal forces within a system, so two objects interacting, forcing each other, don't change the total momentum of the system. That's called the principle of conservation of momentum. Another idea you need to be aware of is what's called impulse, which if a force is acting on an object, that object will receive an impulse. And the size of the impulse is the force multiplied by the time for which it acts. If the force is varying, we can work the impulse out in one of two ways. We can either say, well, it's the average force multiplied by the time, or if we've got a graph of the force against the time, then we'd find the area under that graph, and that gives the impulse. And the most important thing you need to know in dynamics is that impulse is the same thing as the change in momentum. We define the unit of force, the Newton, to make this true. What that in turn means is that if you have only 1 second, then numerically the change in momentum will be equal to the force. So if you want to say, well, what does a momentum of 200 kilogram meters per second actually mean? Well, that means it would require a force of 200 newtons to stop the object in 1 second. And if that helps you visualize what we mean by momentum, then it may be worth lodging that one in your mind. Now that we've looked at momentum, we can look at Newton's laws of motion because they are most conveniently expressed in terms of momentum. So we have the first law: if you don't have an unbalanced force, the momentum won't change. The second law, that the rate of change of momentum is proportional to the force, and we set up our unit of force, the Newton, so it's actually equal to the force applied. This is how we'd write that in equation terms. So we've got the final momentum, m times v. Remember, v is the final velocity, minus mu, u the initial velocity. So this is the initial momentum. Subtract those to get the change in momentum, and that is equal to the force times the time. Remember, we have the change in momentum is equal to the impulse. If we have a situation where the mass isn't changing, so in other words, we haven't got fuel being used up or any relativistic effects, then you will notice that we could move the t to the left-hand side of this equation, and v minus u over t is the acceleration. So we'd have mass times the acceleration is the force, and that is something that you will have encountered in your GCSE courses, and it's something that you can still use at A level. It's a very helpful idea, but please note that technically this is not Newton's second law. Newton's second law is bigger than that, and it involves momentum. The third law, where you've got two objects interacting, the forces acting on the two objects are equal and opposite to each other. In other words, the momentum gain of one object because of the forces will be equal to the momentum loss of the other. So Newton's third law is intrinsically linked to the idea that momentum is conserved in any system. So now it's time to practice ideas of momentum. Further resources up there if you wish, but otherwise just pause the screen or pause the video, have a go at these questions, and there is an answer video below where you see these worked through. While weight may be the most important force you will encounter, drag is also a very important force to know about. It's a force that resists motion. So it will always be directed in the opposite direction to the velocity of the object. The drag gets bigger as you go faster. In some circumstances, it's proportional to the speed. In other circumstances, it's proportional to the speed squared. And when you have objects falling through air, which are typically the scenario that is set in your questions, then the square is the more appropriate assumption. So drag is proportional in that case to speed squared. So you could have something like this. If you've got 2.8 newtons of drag at 21 meters a second, what will the drag be at this higher speed of 35? Because we know that drag is proportional to speed spared, we would write an equation like this and then rearrange it to get the constant. We can then work out the value of the constant using the known data. That's these two numbers here. Once we know the constant, we can then use the equation drag equals kv squared with the new speed in order to get the drag under the new circumstance. This methodology, by the way, is applicable to other problems involving proportionalities, even if they don't involve drag. Drag is also connected to the idea of terminal velocity. When something's falling, you've got the drag, which is nearly always an upwards force with something that's falling. Obviously, something's rising, then the drag is downwards. And you've got the weight that is downwards. When something is dropped from a great height, initially it has no vertical velocity, so v is 0. There is therefore no drag, and the acceleration will be just due to gravity, and as we know, that will be 9.8 meters a second. Let's have a look at the situation in a bit more detail. So here you've got the weight, that's mg, and here you've got the drag, kv squared. So the acceleration will be the resultant force, that's the weight minus the drag, all divided by the mass. So therefore you can see it's g minus this thing, kv squared over m. Notice that really massive heavy objects that have a great big m are going to have a small value of this, and therefore the effect of the drag is going to be less noticeable on a very massive object. So there's the acceleration. Eventually, a falling object, as it falls, will go faster, the drag will get bigger, and this will keep happening until the two forces are balanced and the acceleration has fallen to 0. When this happens, these two things must be equal to each other, or if you prefer, those two things must be equal to each other, and we can solve to get an equation for the speed needed for that to be the case. And we call that the terminal velocity. I know it's a speed, but it gets called a terminal velocity. Here's some practice on drag and terminal velocity. Pause the video, have a go at it, and remember there's an answer video on the same website where you can watch these questions worked through. We've looked at forces that might accelerate or slow down an object. Now we look at forces that might try and turn it. You will probably have come across this idea at GCSE, and we need to extend that at A level. So the moment of a force about a point is equal to the force, there it is, multiplied by the perpendicular distance. That is the distance from the point that we have chosen. And by the way, you can choose any point you like. It doesn't actually have to be a particular place in the plane. As long as you're happy with it, there it goes. And we use the perpendicular distance. We often find it convenient to talk about turning in one direction as plus and the other direction as minus. I've used the convention that this would be a positive moment, an anti-clockwise turning. You can go the other way as long as you are consistent. There's then the principle of moments, which by the way should not be confused with the definition of what a moment is. And the principle of moments is you have equilibrium, that is no turning one way or the other, providing the moments all add up to 0. We do obviously count them turning one way as positive, the other way as negative, and you add all of those up, they come to 0 if the situation is in equilibrium. Notice what we need to do if the force is not perpendicular to our beam, barrier, lever, or whatever it might be, like this situation. So this might be some rod, and then we've got a force being imposed on it by, shall we say, a wire or something like that. If we're trying to work out the moment of that force, remember it is the force times the perpendicular distance, which as you can see here is this distance here multiplied by the cosine of this angle. So there we've got the equation for the moment of this particular force, although you may realise that that's the same thing as saying it is the distance x multiplied by the component of the force, which is at right angles to that beam. You can do it either way, but the equation is the same. A couple, you need to be aware what a couple is where we have two anti-parallel forces that are not on the same point, but they are of the same magnitude, the same strength, and they're separated by some distance, which I've labelled d. The magnitude of the couple is F times d, and it turns out that it doesn't matter where you put a point. I'll just go back there. It doesn't matter where you put a point, the moment of these two forces about that point will be the same. If you have any weights, and you often do have weights when you're solving these problems, always draw the line representing the weight as going through the centre of mass of the object. At A-level, you will deal with the situation where it isn't always obvious which point to choose to use as your pivot, so to speak. You will deal with forces that are not at right angles to levers, and the other big difference at A-level is that you will have situations with more than one unknown force. So here, for example, we have a rod that is 200 newtons in weight, and it's being supported by two support forces, and we are asked to calculate the size of this one. So what we do, in order to calculate the size of this one, we deliberately take moments about a point P here in line with the force we don't care about. Because then the moment of this force is 0, it goes straight through that point, it won't do any turning at all, and therefore this force won't feature in the equation. So we now take moments about P of these various forces. F2, as we said, 0, there's no turning effect of that one. F1 is a clockwise force, we call those negative. The distance between the point and the force is 1.3 metres, so therefore the moment is negative 1.3 times F1, whatever that is. The moment of W, well, it's positive, it's anti-clockwise, it's 200 newtons at a distance of 1 metre, so that is positive 200 units. In this case it's newton meters, but I'll just put the number for now. So for equilibrium, these three must add up to give 0. So in other words, 200 minus 1.3 F1 gives 0, and from that we can work out the magnitude of F1. It's then quite quick to work out the size of F2 if we wanted to, because F1 and F2 together have to add up to give 200. So that enables you to work out the other force. Notice that this one is bigger than that one, and you'd expect that. This one's nearer the middle of the beam, you would expect it to be carrying a larger share of the weight. So here is a set of questions for you to practice. Again, I suggest you pause the video, have a go at these. There's an answer video below. It is the quantity with the question mark that you are being asked to work out in each case. Equilibrium. The two things that need to be satisfied for something to be completely stationary and remaining so are, firstly, there's no resultant force. That means that if you work out the components, you add up all the x components of the forces, they will add to 0, as will the y components, as will the z components. Or alternatively, if you've drawn the forces as nose to tail arrows, they form a closed shape. That means there's no resultant force, there's no net acceleration in any given direction. But in order to show the thing isn't turning either, you also need to choose a point, and it doesn't matter which one, and show that the total moment of all the forces about that point is 0. If your three forces happen to all go through a point, like these three here, then you automatically know that that one is satisfied. The final concept we will look at is the idea of energy and work done. The energy transfer to an object by a force is called the work done on it, and is equal to the force that is on the object multiplied by the distance that it moves in the direction of the force. Another way of putting it is that the work done is the distance times the component of the force that is in the direction of the distance it moves. So if we have a force there and the distance is shown with a d there, and there's the angle between them, we say that the work done, the energy transfer, is F times d cos theta, where theta is the angle between the two. In some cases the force will not be constant, and the work done will be the area under the FD graph. We're now going to look at some examples of energy transfer. The first one, gravitational potential energy. The force, when we're lifting something, has got to balance the weight, and therefore it will be mg. d cos theta, in this case, that is the distance moved multiplied by the cosine of the angle to the vertical, well, that's the distance moved in the direction of a vertical force. That is the vertical distance, which we usually call height. So mg is the weight, that's the force, and the d cos theta is the height. So therefore the gravitational potential energy is equal to the formula that no doubt you practiced for GCSE, mgh. Springs are a little bit more complicated because the force gets bigger as we stretch them more. So we have to use this idea of the area under the line to work out the energy transfer. And because it's a triangle, the area is half times base, that's the extension x, times height, in this case the maximum force F, which is also equal to kx. And as a result, we get this equation here for the energy stored being half kx squared. Now, as soon as I start mentioning half and squared and energy, you're probably thinking about kinetic energy. And yes, you do need to know the formula for kinetic energy is half mv squared. Just want to show you where that comes about. Imagine we've got an object that's going from velocity u to velocity v. Well, the energy is the force multiplied by the displacement. I'll use an s here to link in with what we did in earlier work. So the force is the mass times the acceleration. Now, we're not going to changing mass or anything like that there. So force is the mass times acceleration. So the energy transfer, the work done, will be MAS. But we've already got an equation that 2AS is equal to v squared minus u squared. We got that from earlier. So if we substitute this in, we see that the energy needed to get an object from speed u to speed v is given by mv squared on 2 minus mu squared on 2. If we put u equals 0 to find how much energy it would take to get an object from rest up to that speed, which is after all the kinetic energy, it is half mv squared. Do notice though that if an object's going from one speed to another, we do need to work out the kinetic energies of both speeds and subtract in order to get the energy transfer. Another thing you need to be aware of is power. Now, power is the work done divided by the time taken. You'll be familiar with that from GCSE. But notice what happens in the cases of forces on objects that are moving. So energy divided by time, but we already know that energy transfer is force times the displacement times the cosine of the angle between them. So we can then rearrange it so it looks like this. But S over T is the average velocity at that particular point. So therefore what we have is that the power is equal to the force on an object at a particular time multiplied by its velocity at that time multiplied by the cosine of the angle between them, and that's put in words here. And we can use that, for example, to work out the power of engine needed to move some vehicle against a particular drag force at a particular speed. So, a lot of equations there, so you'll want to practice those. There are plenty of extra practice examples on these Isaac pages, so have a go at those. Pause the video so you can see the questions, and there are worked solutions below when you're ready for them. So that concludes our rapid revision course of mechanics, that is motion, as it is taught in A-level, usually in the Year 12 section. I hope you found this helpful. Remember that you can always come back and revisit not only this video, but any of those questions again, and the individual concept pages if there's any particular area you want to go through because you need a bit more practice. But thank you for taking the time to go through this, and I wish you all the best with your physics and your understanding of science. Goodbye.